Hello everyone. In this lecture I will solve different problems in circular motion and other applications of Newton's law. Let's start here. A race car travels 40 meters per second around a bank which is 45 degrees with the horizontal circular with radius equal to 0.2 kilometers track. What is the magnitude of the resultant force on the 80 kilogram driver of this car? Now here's the race track, this one here, and the angle here equal to 45 degrees. Now the question is, what is the magnitude of the resultant force on the 80 kilogram driver of this car? Now sum of all forces on this one here, it's equal to mv square over r, and this is actually the net force here. Now it's equal to the mass equal to 80, and v in this case it's 40 square divided by the radius for the circular path is 0.2 kilometers, it's 200. And in this case here, the net force or the resultant force on the 80 kilogram driver, it's equal to 64 kilonewtons. An airplane travels 80 meters per second as it makes a horizontal circular turn which has 0.8 kilometer radius. What is the magnitude of the resultant force on the 75 kilogram pilot of this airplane? Now here's the circular path, let's see here, and the radius for this circular path, this one here, it's 0.8 kilometers, and here's the airplane. Now sum of all forces equal to mv square over r, and the net force, which is F in this case, it's equal to 75 80 square divided by 800 or 0.6 kilonewtons, and this is the magnitude of the resultant force on the 75 kilogram pilot of this airplane. An airplane moves 140 meters per second as it travels around the vertical circular loop which has 1 kilometer radius. What is the magnitude of the resultant force on the 70 kilogram pilot of this plane at the bottom of this loop? Now again, here's the situation. And here's the circular path with radius here equal to 1 kilometer here. Now we would like to find the force or the magnitude of the resultant force on the 70 kilogram pilot at the bottom right in here. Now the magnitude of the resultant force on the 70 kilogram pilot of this plane is equal to mv square over r, and in this case here, this is the resultant force, 70 times 140 square divided by 1000, and in this case 1372 newtons is the net force or the resultant force on the 70 kilogram pilot. A car travels along the perimeter of a vertical circle with radius 0.25 kilometers at a constant speed of 30 meters per second. What is the magnitude of the resultant force on the 60 kilogram driver of the car at the lowest point on the circular path? Again, sum of all forces equal to mv square over r, and in this case 60 times 30 square divided by 250 or 216 newtons. A 30 kilogram child rides on a circus Ferris wheel that takes her around a vertical circle path with a radius of 20 meters every 22 seconds. What is the magnitude of the resultant force on the child at the highest point on this trajectory? Now let's see here. Here's the situation. Here's the Ferris wheel, and the child at the top of this Ferris wheel sitting like this. Again, sum of all forces equal to mv squared over r, and v in this case, it's equal to 2 pi r divided by the period. Now v in this case here equal to 5.7 meter per second. Now sum of all forces equal to 30 times 5.7 square divided by 20, or in other words, it's equal to 48.7 newtons. An amusement ride consists of a car moving in a vertical circle on the end of a rigid boom. The radius of the circle is 10 meters. The combined weight of the car and the rider is 5 kilonewtons. At the top of the circle, the car has a speed of 5 meters per second, which is not changing at that instant. What is the force of the boom on the car at the top of the circle? So here's the situation here. And we have a car right here and passengers on this car like this. Now the question is, what is the force of the boom on the car at the top? Now we need to find the force exerted by the circular path on the car at this position. So sum of all forces equal to mv squared over r. Now let's have free body diagram for this one here. We have the weight, it's directed downward, and since the head of the passengers and the car is at the top, so the normal will be like this one here. So mg minus normal equal to mv squared over r. In this case, the normal, that's actually the force exerted by the boom on the car. It's equal to mg minus mv squared over r, and equal to 5,000 minus 500 times 25 divided by 10. The velocity actually is equal to 5 meters per second, and the mass equal to 500 kilogram, and the radius of the circular path, it's equal to 10. You do the math, you will find the normal equal to 3,750 newtons. A 4 kilogram mass on the end of the string rotates in a circular motion on a horizontal frictionless table. The mass has a constant speed of 2 meters per second, and the radius of the circle is 0.8 meters. What is the magnitude of the resultant force acting on the mass? Let's draw the situation here. The circular path and the mass, it's right here. It's connected with string like in this one here. Now sum of all forces equal to mv squared over r. Now the only force we have here is the tension, and tension in this case, it's equal to the mass, it's equal to 4 times the speed equal to 2 square divided by 0.8, or in other words, the tension, it's equal to 20 newtons. A car travels around an unbanked highway curve with radius 0.15 kilometer at a constant speed 25 meters per second. What is the magnitude of the resultant force acting on the driver who weighs 0.8 kilonewtons? Again, sum of all forces equal to mv squared over r, and equal to the mass, it's equal to 800 times the speed, it's 25 square, divided by the radius, it's 150, and simply the force or the resultant force equal to 3,333 newtons. A roller coaster car has a mass of 500 kilograms when fully loaded with passengers. The car passes over a hill of radius 15 meters as shown in the figure. At the top of the hill, the car has a speed of 0.8 meters per second. What is the force of the track on the car at the top of the hill? So what we're looking for here is the force exerted by the track on the car itself. So if we draw the free body diagram here, we have the weight, mg, and we have the normal. And the normal in this case is the force exerted by the track on the passengers. In this case, sum of all forces, it's equal to mv square over r. And in this case, mg minus normal equal to mv square over r. And normal, that's what we're looking for, equal to mg minus mv square over r. In other words, 5,000 minus 500 times 8 square divided by 15, or in other words, the normal equal to 2,866 newtons. A roller coaster car has a mass of 500 kilograms when fully loaded with passengers. At the bottom of the circular dip of radius 40 meters, as shown in the figure, the car has a speed of 60 meters per second. What is the magnitude of the force of the track on the car at the bottom of the dip? Now here's the free body diagram. We have the weight, it's directed downward, this one here, and the normal is the force exerted by the track on the passengers, this one here. Now sum of all forces equal to ma, which is mv square over r, central acceleration, and in this case here it's normal minus mg equal to mv square over r. Or in other words, the normal equal to mv square over r plus mg. You substitute numbers, you will find it's 500 times 16 square divided by 40 plus 5,000. In total, 8,200 Newton. This is the normal force, or the force exerted by the track on the passengers. A 0.5 kilogram mass attached to the end of a string swings in a vertical circle radius 2 meters. When the mass is at the highest point of the circle, the speed of the mass is 8 meters per second. What is the magnitude of the force of the string on the mass at this position? Now we have here an object or mass connected by a string like this one here. Now in this case here, when we draw the free body diagram, we have the weight mg, and we also have the tension in this one here. So tension plus mg equal to mv square over r. In this case here, tension, it's equal to mv square over r minus mg. By substituting numbers, you will find 0.5, this one here, times 8 square divided by 2 minus 5, and it's equal to 11 newtons, and this is the tension. A 0.3 kilogram mass attached to the end of a string swings in a vertical circle with radius 1.6 meters as shown. At an instant when theta equal to 50 degrees, the tension in the string is equal to 8 newtons. Now, what is the magnitude of the resultant force on the mass at this instant? To solve this one here, this is theta equal to 50 degrees. And the tension, assuming this one, this is tension. And this is the weight of the object. It's directed this way here. Now, this tangent here, if this is theta, this one here, this will be theta. And this one will be mg cosine theta, and this one mg sine theta. Now, sum of all forces equal to mv square over r. In other words, t minus mg cosine theta equal to mv square over r. And this is actually the resultant force on the mass at this instant. Now, when we substitute t equal to 8 minus the mass is 0.3 times 10, it's 3 cosine 50. In total, the resultant force equal to 6.07 in the y hat, assuming that this is x and this is y. Now, fx in this case here equal to this one here, mg sine theta, and you calculate this one here, it's 2.3 newtons, and this is Newton, by the way. So the resultant force equal to square root of 2.3 square plus 607 square, or equal to 6.5 newtons. An object attached to the end of a string swings in a vertical circle r equal to 1.2 meters as shown. At the instant when theta, this theta, equal to 30 degrees, the speed of the object is 5.1 meter per second, and the tension in the string has a magnitude of 20 newtons. What is the mass of the object? Now let's have free body diagram. This is the tension right here, this tension, and the weight of the object is this one here. Now if this is theta, this will be 90 minus theta, and this will be theta. In this case, you analyze the weight mg cosine theta, and you analyze the weight in this one here, it's mg sine theta. In this case here, tension plus mg sine theta equal to mv square over r. 20 is the tension, plus 10 over 2 m equal to m times 5.1 square over 1.2 is the radius of the circular path. Now you solve this one here, you will find the mass of the object, it's equal to 20 divided by 16.7, or the mass of the object, it's equal to 1.2 kilograms. A 0.4 kilogram mass attached to the end of a string swings in a vertical circle having radius of 1.2 meters at an instant when the string makes an angle of 40 degrees below the horizontal. The speed of the mass is 5 meters per second. What is the magnitude of the tension in the string at this instant? Now let's draw the situation here. Here's the circular path, and this is the radius for the circular path, and it making this 40 degrees below the horizontal, and we would like to find the magnitude of the tension in the string at that instant. So let's again have a free body diagram. This is the object here. So we have mg directed this way here, and this is the tangent. So if this is theta, which is 40, this will be theta as well, and this will be 40 as well. So if this is 40, this will be 50 degrees. Now you analyze this one here, mg cosine 50, and this one right here, it's mg sine 50. Now in this case here, tension minus mg cosine 50 equal to mv square over r. So tension equal to mv square over r plus mg cosine 50, or equal to 0.4 times 25 divided by 1.8 plus 0.4 times 10 cosine 50. In other words, the tension equal to 8.1 newtons. A 0.5 kilogram mass attached to the end of a string swings in a vertical circle with radius 2 meters. When the string is horizontal, the speed of the mass is 8 meters per second. What is the magnitude of the force of the string on the mass at this position? Again, let's have circular path like in this one here, and the string in horizontal position like in this one here, and here's the object. In this case here, we have the weight, it's this way here, and no other components because this is x and this is y. So the only component for the central force is the x component. It's the tension in this case. So tension equal to mv square over r, or equal to 0.5 times v. In this case it's 8 square, it's 64, divided by 2, in other words it's 16 newtons. An airplane flies in a horizontal circle of radius 500 meters at a speed of 150 meters per second. If the plane were to fly in the same 500 meter circle at a speed of 300 meters per second, by what factor would its centripetal acceleration change? Now in this situation here, the speed of the airplane, it's 150 meters per second and rounding around horizontal circle with radius 500 meters. If the speed is doubled, what's going to happen to the centripetal acceleration? Now to find this one here, let's calculate the centripetal acceleration in stage 1, which equal to v square over r or a, in this case let's name it a1, equal to 150 square divided by 500. Now a1 in this case equal to 45 meter per second square. Now a2, same rule, it's v square over r, or a2 equal to 300 in this case, the speed is doubled, square divided by 500 meters, or it's equal to 180 meter per second square. Now A2 with respect to A1 is equal to 180 divided by 45, and in this case A2 equal to 4A1, which means if the speed is doubled, the acceleration will become 4 times. An airplane flies in a horizontal circle of radius 500 meter at speed of 150 meter per second. If the radius were changed to 1000 but the speed remained the same, what factor would its centripetal acceleration change? Now same question as before, but in this case here the radius is doubled and the speed remains the same. We want to find what's going to happen to the acceleration if the radius of the circular path is doubled. So let's start in stage 1. A1 it's equal to v square over r and it's equal to 45 meter per second square. We just calculated this one in the previous example. A2 equal to v square over r, or 150 square, remember the speed remains the same, divided the radius is doubled, it's 1000, and in this case A2 equal to 22.5 meter per second square. Now A2 with respect to A1, it's actually equal to 22.2 divided by 45, and in this case A2 equal to half A1, which means if the radius is doubled, the acceleration will drop by half. An airplane flies in a horizontal circle of radius 500 meters at a speed of 150 meters per second. If the plane were to fly in the 1000-meter circle at speed 300 meters per second, by what factor would its centripetal acceleration change? Now in this case here, the radius is doubled and the speed is doubled. What's going to happen to the acceleration? Let's do the calculations. A1 in this case, it's v square over r, and we just calculated this one in the previous example. It's 45 meter per second square. A2 equal to v square over r. In other words, A2 it's equal to 300 square over 1000. In other words, A2 equal to 90 meter per second square. Now A2 divided by A1, it's equal to 90 over 45. In other words, A2 it's equal to 2A1. This actually means that if the radius is doubled and the speed is doubled, in this case the acceleration will be doubled. A 50-kilogram child riding a Ferris wheel with radius 10 meters travels in a vertical circle. The wheel completes one revolution every 10 seconds. What is the magnitude of the force on the child by the seat at the highest point on the circular path? Now here's the situation. We have a Ferris wheel, this one here, and this is the seat, and this is the child, and remember the head of the child is up. Now when we draw the free body diagram here, we have mg and we have the normal, which is the force exerted from the seat on the child. That's actually what we're looking for. Now sum of all forces equal to mv square over r. In this case mg minus normal equal to v square over r. Now to calculate v, remember from the equations of motion, x equal to vt, and x it's one revolution and t 10 seconds. One revolution, it means v equal to 2 pi r over t, when you calculate this one here, you will find V equal to 2 pi times 10 divided by 10, or in other words, it's equal to 6.28 meter per second. Now you substitute this V back in this equation here, you will find the normal force equal to mg minus mv squared over r, or 500 minus 197. In other words, the normal force, or the force exerted by the seat on the child at the highest point, equal to 302 newtons. That's it. Thank you for watching.